Just two more modules. One is on cyclones and then monsoon. So I wanted to end with monsoon because that is one of the important players when it comes to India. So before I move to cyclones, just wanted to tell you the difference between this MJO and MESO. I'm not sure how many people have heard about this MESO, which is monsoon intraseasonal oscillation. But this has a very important bearing on monsoon. And the reason, and like I said, if you go back to our discussion this morning, MGO is very active during November to April. It plays a primary role. The reason it doesn't play a very primary role during May and October is because of the presence of this MESO, which is the monsoon intraseasonal oscillation. And I don't want to spend too much time, but I just want to show this one plot. Both of them are actually air-sea coupling. But MESO is much more complex because it is the air-sea coupling, plus it has to account for the ITCZ movement, which is the intertropical convergence zone, which starts moving north during the onset of monsoon. So starting from May, this ITCZ moves northwards, correct? So this MESO has a very distinct feature where it moves from west to east, just like MJO, but at the same time, it also has a north and south movement, okay? So that is one of the important points that makes MESO very interesting, because it not only moves near the equator, but it also moves along this meridional direction, which is north and south. Okay, and IITM Pune has an extremely nice MESO forecasting, and it only puts out this forecasting between May and October. So only during the monsoon period, this MESO is present, because now if you look at the IITM website, this MESO is not present because it doesn't make sense, because ITCZ is not moving at all, right? ITCZ is not moving at all in the sense it is not favorable for a monsoon system. So if you can see this particular plot during August, you can see that blue is the active phase of MESO, red is the weaker, is the break phase of MESO. So what happens is I'm always on the lookout for this active phase of MESO, which is this blue color. And I always want to see where is this blue phase, and that is going to tell me where the monsoon is going to be active. And if you look at this, the monsoon is active over central India and west coast of India in around August period. And again, once again, this MESO is only as a guidance, but it gives a very interesting aspect of how the monsoon break and active phases are going to come towards India. And what IITM has done is it has divided into phases, and each phase is actually named. You can see North India and foothills and South Indian Ocean, South Indian Ocean and Indian Ocean. Indian Ocean is North Indian Ocean. Then the South Peninsular India, Central India. So it has given phases. So we are always on the lookout for in which block this MESO is in. Because if the MESO is over peninsular India, then Kerala will get heavy rains. Okay, whereas if the MESO is over central India, then the Konkan coast will get massive rains. Konkan coast plus interior Maharashtra will get very heavy rains. When this particular MESO shifts to foothills of Himalayas, then the Northeast India and Northern India, like UP, Bihar, Northeast India, and parts of North India will get rains. So this is the overall picture by looking at MESO, which you can derive, which is a very interesting thing, I believe, because this is the large-scale circulation of monsoon, which is very important for understanding the active and break phases of monsoon. Okay, I forgot that
Two quick questions on the MESO, please.
Yeah, please.
So the MESO is synonymous with the monsoon trough, right?
The monsoon trough is the MESO, correct.
And secondly, in the IITM chart, one of the quadrants showed South Indian Ocean. So during the summer monsoon, how would the monsoon be active in the South Indian Ocean?
So basically, that SIO and Indian Ocean is basically the not South Indian Ocean in the sense that it is starting from equator to the Indian Ocean. That's all. So of course, okay. Yeah. So it is starting from MESO. Usually the forecast starts from the equator and it moves up north. That's all. So you can see that during monsoon, most of the South Indian Ocean is is completely inactive, right? It's only the Indian part which is very active.
So this would refer to regions around, say, Sumatra?
Yes.
Okay, thank you.
Sir, is the direction of meso similar to MJO, sir? What is the direction of meso, sir?
So meso moves west to east and also north. So it moves from let us say Somalia to Sumatra or even further to South China Sea. But at the same time, it also moves north. That is what is very important. So if you look at the meso chart, then you can slowly see that. So this is that entire span, and you can see that this is also moving eastwards. So see, so there's an eastward movement as well. So it has a direction similar to MJO, but on top of MJO, it also has a northward movement, which is very important for monsoon. MJO doesn't give that. So that's why MJO is not a good indicator during monsoon season.
Okay, sir.
Sorry, so there is one more topic, which is the El Nino and La Nina, which I forgot. So maybe we will try to cover that as well. So along with these latitudinal cells, which are the Hadley cell, which we saw, you also have something known as longitudinal circulation cell, which is the Walker cell. So Walker cell occurs at one particular latitude, which is close to the equator, and it is a longitudinal cell which extends along the ocean. So it extends from one end of the ocean to the other end of the ocean. And that Walker cell is very important because the strengthening of the Walker cell is what allows the agencies to explain or kind of tell whether the ENSO phase has coupled with the atmosphere or not. So Walker circulation cell is nothing but a complete circulation cell in the atmosphere, which is over the ocean, and which actually tells whether the ENSO has coupled or ENSO has not coupled. And same with IOD also, Indian Ocean Dipole. Okay, so this is not a meridional circulation cell; it is a longitudinal circulation cell extending along the longitude from eastern, let's say Western Pacific, all the way to the Eastern Pacific. So it has different phases. We will talk about that when we talk about ENSO. So ENSO is basically the El Nino Southern Oscillation. So in a very simple terms, let us not get into the background because we don't have much time. But it was Walker who actually found this El Nino phenomenon for the first time in 1910. What he did was he looked at these pressure charts, again looking at the pressure charts, and he saw that in the Western Pacific, sometimes what happens is the pressure over Australia changes to low. There is a seesaw in the pressure difference between Australia and South America. Okay, and then that's how he gave this term, which is Southern Oscillation. And at the same time, what people also observed was that in the ocean, there is anomalous warming and anomalous cooling along the Pacific Ocean. So this El Nino is a coupled ocean atmospheric phenomenon, which actually starts from the ocean and gets coupled into the atmosphere. Okay, so let us look at what is this El Nino Southern Oscillation. So what happens is during normal time, there is warmer water over Australia and there is colder water over South America, which creates a Walker circulation cell, which has an ascending branch over Australia and which has a descending branch over South America, thereby giving a lot of rains to the South Asian countries as well as Australia. Now, during the phases of El Nino, what happens is the warm water from here moves to South America and the cold water from South America moves to Australia, thereby changing the direction of the Walker cell. So now the Walker cell direction changes where the ascending limb is over South America and the descending limb is over Australia. So the reversal of Walker cell is what we call as El Nino. So this is the El Nino. So you can see that the Walker circulation cell has reversed. Okay, so now there is a descending branch over Australia and an ascending branch in the Central Pacific. Whereas this is the La Nina, where the Walker circulation cell actually strengthens in the sense that it becomes much stronger compared to its normal state. So the normal state of Walker circulation cell in the Pacific is ascending branch over Australia and descending branch over South America. When it strengthens, So when the pressure over Australia drops further down, then it means that there is a signal that La Nina is going to emerge. When the pressure signal over Australia increases, then that means that there is a possibility of El Nino. So this El Nino and La Nina are basically governed by the movement of the water along the Pacific, between the Western and Eastern Pacific, and the associated Walker circulation cell that forms in the atmosphere. Okay. So if there is a very nice movie which is present in this particular, I have taken it from YouTube. So it nicely explains. It is from the Climate System Science.
El Nino and La Nina events, collectively known as ENSO, generate profound year-to-year changes in weather patterns around the world.
So I will share this with you, and you can see
Using
that
a supercomputer, we have recreated the strongest El Nino on record in late 1997 that was followed by 2 back-to-back La Ninas. The heart of ENSO is in the vast tropical
Pacific.
Pacific.
Is the Australia where there's
Much of the action occurs below the surface.
Warm water.
To see this, we focus on a
there is
300-metre deep slice of the ocean along the equator.
And slowly this warm water will move.
A massive
here.
pool of warm water sits in the west.
So this is the normal state. This is the normal state of the ocean. And this is for El Nino to form. I don't know why it is not moving.
Cools, and the warm pool reforms in the west.
So this is La Nina, where the warm water is getting warmer and warmer. Thereby
this
the
temperature contrast across the equatorial Pacific is linked to the westward blowing.
And if you look at El Nino, I think I will share this video. You can take a look at it. See, during El Nino, what happens is,
by peeling away the ocean surface, we can see how ocean currents move heat around into the Indian Ocean through the Indonesian archipelago.
So you can see that now the warmer waters have collected over South America. I'm just trying to find this El Nino.
Changes.
Just give me 1 second here. Yeah, so this is El Nino where the warmer water is now so this is the classic El Nino where the warmer water shifts to South America and the colder water is over Australia, and this actually leads to the reversal of the Walker circulation cell. And these are the patterns that we are on the lookout for. Okay, so ENSO cycle, there is a cycle which used to be there. If you look at the record, then after every El Nino there has to be a La Nina. So you can see that they come in phases, but over the years, with climate change, you can see that this pattern has been disrupted, where you are now seeing longer periods of El Nino and shorter periods of La Nina. And this is the classic example where you saw El Nino persisting for a very long period of time. And now also we didn't have a La Nina after 2013. 2013 was our last La Nina year, and now 2020 is the by La Nina I mean strong, moderate or strong La Nina. So 2013 or 2012 was the last strong La Nina. After that, after 8 years, we are producing a La Nina. So the ENSO cycle, so El Ninos have increased, whereas La Nina has decreased. The reason people are pointing it mainly because of the way the ocean is responding towards this the global warming that we are putting into the atmosphere. Okay, so this cycle is something there used to be a pattern, but that pattern is getting disrupted. So we need to understand that particular pattern. I'll skip this. These are things which I don't think we need to get. So how is the El Nino and La Nina characterized? So El Nino is characterized by looking at something known as a Nino 3.4 index, which is the region in the Pacific, which is this particular region. So what climate scientists do is they look at the temperature variation over a period of 1 month or over a period of 3 months in this region, and they come up with a 3-month average. And whenever the 3-month average sustains, so minus 1.5 means lower than normal temperatures in this region. Okay, and red means higher than average temperature over that region. So lower than average temperature in that region means La Nina. So the blue means La Nina, and red means El Nino. And they look out for this index. It should, if it sustains for 5 consecutive months. Okay, so if you see this index in red, which should have a value of greater than 0.5. If you see this index for consistently for the 5 months. Then they signal that El Nino watch. They give a El Nino watch. So there is a watch, then there is an alert, and then there is a El Nino announcement or a La Nina announcement. Okay. So this particular anomaly should sustain itself for consecutive 5 months. Then only ocean and atmosphere will couple itself, and an El Nino signal, full-fledged El Nino or La Nina signal would have emerged. So climate scientists usually look at this particular period, this particular area, to announce whether an El Nino or La Nina is going to form or not. And why is the El Nino not good for India? The reason is because from this All India Summer Monsoon Rainfall from 1817 to 2018 or 2015 they have taken, and they have seen that most of the this is La Nina. Most of the La Nina years are associated with above normal rainfall, and most of the El Nino years are deficit. So you can actually correlate this this red circle and the whites and the green and the blue circles, and you can see that El Nino is bad, whereas La Nina is good, except some years, which this is 1997, when it was a very strong El Nino, but rainfall was normal, mainly because of the presence of IOD. So around 1997 is when people started looking at the Indian Ocean Dipole, which is the counterpart of El Nino. Okay, so I'll go to Indian Ocean Dipole, but before that, I just want to show you this average annual temperature of an ocean, of the Pacific Ocean, which is actually increasing over the past few years, triggering strong El Nino and longer El Ninos. The phases of the cycle of ENSO is now favoring more towards El Nino than La Nina. That's what I'm trying to tell you. Okay, so we should embrace ourselves for more El Nino type of events compared to La Nina type of events, because that is what the statistics is saying. But that doesn't mean that our monsoon will be deficit. In the last 2 years, we have seen that. 2019 was a classic example of a very excess monsoon, even though El Nino was present last year. And that is what pushed the scientists to find out this other phenomenon in the ocean, which is the Indian Ocean Dipole. This Indian Ocean Dipole is a very local phenomenon to Indian Ocean, which is between the Somalia coast and the Sumatra coasts. Okay, it is very similar to ENSO, but it occurs in the Indian Ocean. Hence, it is called Indian Nino. So let us look at this Indian Ocean Dipole. So during the normal Indian Ocean Dipole, the neutral phase of Indian Ocean Dipole, what happens is you have a colder water near Somalia and you have warmer water near Sumatra. So that kind of gives favorable rains to or more rains to Southeast Asia compared to India during the neutral phase. But during Indian Ocean Dipole phases, neutral Indian Ocean Dipole phases, India gets normal rainfall. Okay. However, during negative phase of IOD, the cooler water becomes more cooler and the warmer water becomes more warmer, thereby triggering a stronger Walker circulation cell near Southeast Asia or Australia. So negative phase of IOD is mostly favorable for Australian region, and thereby Indian region gets a deficit. Okay. So then you have the positive phase of IOD, where during the positive phase of IOD, what happens is the West Indian Ocean or the Somalian region becomes warmer than normal, and this becomes cooler than normal, and that drives a strong Walker circulation cell that gives a lot of rain to the Indian subcontinent. Okay, so these are the three phases that scientists have actually given, and recently what people are saying is the Indian Ocean Dipole is a more correct representation of rainfall over India, and that is the reason why a lot of research is being done over Indian Ocean Dipole. And when you talk about Indian Ocean Dipole, you have I'll skip the dynamics. You have this IOD signature. So what scientists are doing is they are trying to find this IOD signature in a period of 1 year. They are seeing when the IOD becomes positive and when the IOD becomes negative. So this above plus 0.4 is a positive IOD, below negative 0.4 is a negative IOD. So they're on the lookout for these kind of positive IOD events, because that means that even if it's an El Nino year, the Indian Ocean Dipole will make up for it by giving more moisture from the Indian Ocean. Because previously it was thought that most of these moisture is coming from the Pacific. Even for the monsoon systems in India, most of the moisture is coming from the Pacific, which was true probably 2-3 decades back. But now the warming of the Indian Ocean has actually changed the dynamics, and most of these moisture that we are talking about, more amount of moisture is coming from the Indian Ocean compared to the Pacific, and that is one of the important aspects of monsoon which we need to embrace. Okay, so what we are now doing is we are actually putting a IOD record where we see these phases of IOD which were and when this IOD peaked and when it did not, and we are actually putting together what happened during these years when IOD was very strong. And there is a very strong teleconnection that whenever the IOD values have been strong, which is 1994, 1997, and the recent one 2019, there has been heavy rainfall over India. Okay. The second thing that we are seeing is negative IOD. Even though negative IOD is not good for India, but when the negative IOD actually coincides with the La Nina year, then we actually have a very strong rainfall. So which happened in 2012 when there was a negative IOD, but we also had a very strong La Nina year, and hence it was a good monsoon year for India. And same thing in 2020 also, neutral IOD, but we had a very strong El Nino or moderate La Nina this year, so it helped in a good rainfall. So what I'm trying to say is that now now the climate scientists are actually putting IOD plus ENSO plus other features together to actually give the performance of the rainfall over the period of 3 months. Okay, and that is why revisions are being done every year because new metrics are emerging for monsoon. So hence we have to be very clear that this is not. I mean, this is still a work in progress. That the how much rain we get from monsoon is still a work in progress. Okay, so but these are the indices which one should look at before committing to anything about the performance of the monsoon. And IMD has a very good handle on all these signatures, and whatever they actually forecast, most of the time it happens because they look at this complete picture rather than just looking at El Nino. And some of the agencies, private agencies in India, they actually have made a claim that ENSO is the only phenomenon which, by looking at ENSO, we can understand Indian monsoon. These kind of statements are extremely dangerous because it's not true. Okay, so it's very important that we understand these things, and we don't. I mean, so IMD has a very good handle, and that's why I think we should have more trust on what IMD tells us rather than these other private players in India, whose forecast is not as good as IMD.
Sir,
So here I'm just showing a 2019 record, and this was So this was an article that I wrote for the Weather Channel. It was in May 2015. So this was actually this came true because 2019 was not a very strong El Nino year, but was a moderate El Nino year, and that was a time when one of the private agencies in February had announced that the monsoon 2019 is going to end in a deficit, and that was purely based on the El Nino thing. El Nino is going to make the system, make the monsoon poor. But then the Indian Ocean Dipole aspect was completely ignored, and this is when I thought that it's important that we tell. This kind of information should not be proliferated. So then I introduced this idea of Indian Ocean Dipole in an article, and it ended up that 2019 actually ended up as a positive, very strong Indian Ocean Dipole here. And these kind of metrics that I talked about actually help us in understanding how IOD is going to develop. And if you are on the lookout for these signatures, then you can actually make a decent prediction about monsoon. So although it was, IMD and many other weather bloggers predicted that 2019 would end up as a normal year, which is 100 to 105%, but it ended up in 110%. But still, that is good, because what I'm trying to say is saying below normal and getting excess is bad than saying normal and getting excess. So because when you say below normal, then there is this the farming community and agricultural community in India becomes, there is a negative thing that gets set in their mind, and it's not actually very good. So we have to give a decent forecast, and the most likely forecast looking at all the complete picture rather than only looking at El Nino. So the whole reason about this particular module was to tell you that El Nino is not the only thing that actually governs the monsoon. There is Indian Ocean dipole, and on top of that, there is also this monsoon circulation, which is very local to India, which we don't understand very carefully. That circulation, we don't understand it very well. So these three things are the ones we should actually pay attention. ENSO, IOD, and how the monsoon circulation cell actually sets up. And the setting up of this monsoon circulation cell is actually related to the Siberian cooling that I talked about, the Tibetan plateau heating that I talked about, and how the jet stream moves up. So all of these are actually should be put in a framework, and then only nice forecast about monsoon should be given, which IMD does. I know for a fact because the reports clearly mention that. Okay, so any doubts before we have a very quick session on cyclones, and then I want to spend at least half an hour talking about monsoon.
Sir.
Okay,
sir, can I ask one doubt, sir?
I mean, so cyclones, we know that they are rapidly rotating mass of air, and there are different names. So the only thing that I want to talk about cyclones
questions on the ENSO.
What is the fuel? Okay, so what is the fuel for a cyclone? So the main fuel for a cyclone is the sea surface temperature, which is 27, which should be greater than 27. Actually, 28 degrees is what now we are saying. It should be greater than 28 degrees. The ocean heat content should be greater than 100 kilojoules per centimeter squared. This is measured as the energy stored in the ocean in the top 1,000 meters. How it is done? It is done using the data that we have up to 100 meters, and then the next few meters, we know that ocean is in a quiescent state, so we don't take that much into account. But the thermal energy stored in that top 500 meters is very important, because that is what is going to give energy to the atmosphere. Low wind shear and the Coriolis force. These are the four important aspects. So there are the places from which you can actually get all these values. Okay, I will show how from where in the afternoon session. It has three distinct features: eye, eyeball, and the rain bands. So I'll just quickly touch upon them. So the eye of the cyclone is the calmest portion of the cyclone. The reason is because in the eye, whatever air is updrafted, it condenses and falls down as cool air. Okay, so eye of the cyclone is the clear and the calmest part of the cyclone, but the pressure is the lowest in the eye of the cyclone. So that is what is the powerhouse of a cyclone. If the pressure falls, then it will actually take in a lot of moisture, and it will allow updraft of the moisture. So the eye of the cyclone is mainly known for the lowest pressure, but in terms of cloudiness and winds, it is the calmest. So then which is very clear because we see the eye of the cyclone from in satellite images, and then we can then we see that it is a very clear part without any clouds. Okay. So the most destructive part of a cyclone is the eyeball. That is the most dangerous part of a cyclone. We all know why, because it carries the strongest convective bands, and it has strong winds. And more compact the cyclone, more dangerous it is. Again, you can prove it from the conservation of angular momentum. If it is more compact, it will rotate very fast, and rotating very fast means it will actually have high vorticity, and high vorticity means it will take in a lot of moisture, and it has the capacity to become a very strong system. So this is something that I wanted to put in the life cycle of a cyclone. All these cyclones start as an equatorial hotspot very close to the equator. So they start off as a vortex. Okay. So what is this vortex? It is a disturbance. It is a disturbance. So it is very similar to a wave. So a wave which has passed by in some region of the ocean, can it create that vortex in the ocean or in the atmosphere, just 1 meter above the atmosphere? If it has created that, then that is the starting point for a cyclone. And if the fuel is high, the fuel is basically the sea surface temperature, the ocean heat content, the wind shear, and Coriolis. Coriolis is always present, so we don't care about the Coriolis. So if other three things come into picture, then that particular small disturbance that is present in the ocean will become a low pressure system. That low pressure system, if the fuel is maintained, it will become a depression and then become a cyclone. And this fuel, if it is sustained for this long period of time, that is known as the Genesis potential index of a cyclone. So for the Genesis potential index, the vortex, a hotspot should be there, followed by the fuel, which takes it to a cyclone level. Once it goes, then if the fuel is present, then it will intensify, and then it will maintain a status and then approach land and dissipate. So what we are always on the lookout for is we are on the lookout for MJO, which has the capability to plant this seed. We are on the lookout for MJO. We are on the lookout for wave action, which is Rossby wave most of the time. We are on the lookout for so these are the two things. MJO and Rossby waves are the things which can actually put in this seed, which is required for cyclone formation. After that, if a seed has formed, then we are on the lookout for these other parameters like the ocean heat content, the ocean temperature, and the wind shear to see if this particular seed can become a cyclone or it will die off as a low pressure system. Okay, so that is what is the Genesis Potential Index. Like I have written here, the Genesis Potential Index of a cyclone is gauged by MJO and the wave action. And sometimes it is also gauged by the intraseasonal oscillations, which is kind of the Indian Ocean Dipole and El Nino. But I'm not going to touch upon that because that's a little bit more complicated. But these two are most of the time the things that actually plant the seed for formation of the cyclone. Okay, so let's say the cyclone has formed. Once the cyclone has formed, how do we track the cyclone? So that is a very important aspect because I know how a cyclone forms. Okay, so then I need to find out how the cyclone is going to move. So the movement of the cyclone is governed by these two things, which is the Indo-Arabian Ridge and the Indo-China Ridge. So there are two ridges. So the ridge is nothing but at the 300 millibar chart, you will see a high pressure system. Okay, those two. So this is the ridge. So if you look at the IMD GFS output, you will see that at 300 millibar or 300 HPA level, I see these two anticyclones, which are high pressure zones. Okay, so these two zones, these two high pressure zones are going to govern the track of the cyclones because cyclones tend to move along the ridges. Okay, cyclone tends to move along the ridges. So this Indo-China ridge is the ridge which actually gives the cyclone its northward track. And this Indo-Arabian ridge is the ridge that gives it the westward track. Okay, so when a cyclone is governed by the Indo-China ridge, then it has a tendency to move north. That is why during April, May, most of the cyclones move up north because they are governed by the Indo-China ridge. So either they go to Odisha or they go to West Bengal or Bangladesh or Myanmar. Indo-Arabian ridge is the ridge that actually takes most of the cyclones away from the Indian coast towards Oman or Somalia. Okay. So maybe there are a lot of things I just wanted to talk about, but maybe I will skip these things and I'll just come to one point again about these things. You can read up because I'll be sharing it anyways. You can read it up. A common thumb rule. This is something important because if you are interested in tracking a cyclone, then this is something that may come handy. This is what I have observed. So during April and May cyclone seasons, the Indo-Arabian ridge is far to the west. Hence, most of the cyclones that form near the Indian subcontinent, they have a tendency to move northwest under the influence of Indo-China ridge. So during the April-May seasons, Indo-Arabian ridge doesn't favor any much. It's the Indo-China ridge that governs the cyclone, and hence they have a northward track, okay, or northwestward track. On the other hand, the cyclones that form in the Arabian Sea during April and May, they move towards Oman coast because they are governed by the Indo-Arabian ridge. However, if you look at the September to December season, then both the ridges are close by. So they are very near to India, and hence most of the time what happens is they initially have a northwest pattern, and then they have a west-southwest kind of a pattern. So I'm going to take two examples. Cyclone Fani, which was a category 4 cyclone, extremely severe cyclone. The Indo-China ridge played a very important role because the Indo-Arabian ridge was far away, and hence the cyclone Fani had a fully northwest track. So it started from equator. You can see it simply moved towards the north. Okay, so it was fully governed by the Indo-China ridge because the Indo-Arabian ridge was very far away. There was no influence of that. This was in May 2019. Then you have Gaja, which is a cyclone which formed in I think October 2018. If I'm right, I'm not sure whether it was October or November, but it's okay. Both the ridges were very close to India. So initially, it came as a remnant of a storm from South China Sea, and initially it was governed as a northward track, which was due to the presence of the Indo-China Ridge. And then there was a handshake between the Indo-China Ridge and the Indo-Arabian Ridge, because this Indo-Arabian Ridge was also present. So the cyclone kind of waned its influence of Indo-China Ridge and now started to get influenced by the Indo-Arabian Ridge. And the interesting thing about Gaja, which is a very, something even I don't know why it was. It stood in this region for 24 hours and it made a circle. So you can see that there was an inertial loop. It simply made a circle here before it was completely governed by the Indo-Arabian Ridge. And then after that, once it was governed by the Indo-Arabian Ridge, it just kept moving towards Somalia. So it was fully a full west-southwest track. You can see that it is not moving north, it is moving west. So Indo-China Ridge usually takes cyclone to the north, and Indo-Arabian Ridge usually takes cyclones to the west. So this is something which is very important. And during the April-May seasons, Indo-China Ridge is very active because Indo-Arabian Ridge is very far. However, during November and December, both the ridges are very close by, and hence most of the cyclones, Varda also had a very similar track where it just came flat, okay, because it was fully governed by the Indo-Arabian Ridge, okay. One other thing is, if you talk about Cyclone Nivar didn't follow a westward pattern; it moved north. It had a north-west pattern. The reason is because Cyclone Gati was forming at the same time, and Cyclone Gati ensured that this Indo-Arabian Ridge moved away from India. So Cyclone Nivar was kind of governed by the Indo-China Ridge. Because I said that's very common for storms in November and December to have this kind of a pattern. But there can be some differences, because if a cyclone forms, if there are two cyclones which form around the same time, then the ridge action gets ridge action gets changed, and because of that, your movement of the cyclones will also get changed. So that is if Gati had not formed, then the Indo-Arabian Ridge would have been near India, and that would have not allowed the system to move towards Pondicherry, but it would have allowed the system to move more towards southern part of India, southern part of Tamil Nadu.
A question about Nivar and Burevi.
We have a very good track record of cyclone prediction. This is something that was given by WMO, which is the World Meteorological Office. India has a very, very good track record of cyclone, because we understand a lot of things about cyclones, how they move, how the ridge actually governs the movement. A lot of things we know about cyclone, and hence I think we are ready for any kind of cyclone prediction, be it a very super cyclone or be it a cyclone like Nisarga. Both of them, I mean, we can predict, and we are ready for evacuation and all these things. So mitigation. So if there is any doubt, I can, before I move into monsoon.
There is a question. Hello. Hi. Hello. Hello.
Hello.
Professor Sridhar, there is a question about Nivar and Burevi.
Yeah.
Nivar, actually, what happened was that there was some expectation of destructive winds close to the coast, because of low wind shear. But what happened was towards the end, when it was nearing the coast, the wind shear suddenly appeared to increase. No one could have predicted that, but it was good, because in the end we had only rains but no destruction. And also regarding Burevi, what happened? It stayed as we used to say, the uninvited guest in the Gulf of Mannar for several days, giving incessant rains to Delta region. The Kaveri Delta region. For a long time, probably because neither of the two ridges cared about the circulation, and nobody took control. So it appeared to just get stalled for a while. mean, could you comment on why? I only wanted to know why we are not able to predict the wind shear pattern. What is going to happen next? Because we were expecting that there's going to be some destruction with Niver, but nothing happened. That's good. But at that time, just I was tracking this for a long time, and I just got exhausted and slept off. The next morning I woke up, there was absolutely no problem.
Right. So that was actually expected, and I think more than the wind shear for Nivar, more than the wind shear, it was to do with the pattern of, with the system itself. And I'll just focus your attention here to this particular chart. So one thing is this particular cyclone Nivar was a very severe cyclonic storm.
Yes.
And generally, very severe cyclonic storms, what they do is they usually form a very clear eye, so they become more compact and compact. But with Cyclone Nivar, what happened was it couldn't become more compact, and the reason was because it kept getting hindered by the presence of topography. So first, it was the North Sri Lankan topography that interacted with the southwestern bands of Nivar. And then later on, it was a delta region that kind of interacted with the western bands of Nivar, right? So the cyclones, even though it's a very severe cyclonic storm, because the winds were very strong at near the eye wall, okay. But the interesting thing about cyclones is, if you come outside of the eye wall, the winds actually drop exponentially. So this is what I wanted to show you. So winds drop exponentially. So near the eye wall, the winds are strongest, and as they move away, the winds drop exponentially. And for a cyclone which is very well organized, for a compact cyclone like this, which is showing a very clear eye, if you draw this particular diagram, you will see that the exponential decay is not very strong of the winds. So let us say from 150 kilometers per hour, it will drop to 100 kilometers per hour near the end of the cyclone, outer band of the cyclone. But for disorganized cyclones like Nivar, this particular drop is going to be massive. And what we feel during the cyclones, as the cyclone is approaching, the first thing we feel is these winds. So more than the wind shear, because the wind shear is just one aspect, and I think the wind shear is not the right. I mean, it is one of the metrics, but we don't have a very good handle on what exactly is the exact value of the wind shear. But a better thing is organization of a cyclone. So Nivar never had opportunity to get organized because of the topographical effect from Sri Lankan topography and also from the delta topography. So the winds actually never could. So the cyclone could never become compact, and that was one of the reasons why you did not expect. And it was expected that even if it is a very severe cyclonic storm, the damage will not be too much, because the cyclone never could organize even before landfall.
Yeah. Okay. Thank you. That was informative.
Right. So Burevi was a very. I mean, I'm still not very. I'm still in awe of Burevi, because it was something. I mean, for a cyclone giving, it was more of a depression, I would say. Like although
Yes.
it attained a cyclone status, but it behaved like a depression which kept giving rains for almost 7 or 8 days continuously. And I'm not too sure what happened there, but it would be interesting to do a case study on that.
Okay.
Yeah.
Sir, can you please tell about that Walker circulation once again, sir? How it dominates the El Nino and La Nino, sir?
Okay. Can I do it later? Right now,
Yes, sir.
I think
No
we
problem,
can this monsoon, because
Yes, sir. Yes, sir.
we-
And the
we-
Burevi, on question, sir, Burevi did not give rains to southern parts of the Tamil Nadu, sir. Even though it was near Ramanathapuram, nearby Thoothukudi district did not get rains, sir.
Oh, that
Only the
was
northern parts,
yes.
like Delta, Kaveri Delta, Tanjavur, through our districts are getting heavy rain. Kadalur also was getting very heavy rain, sir. What would be the reason? Nearby Kanyakumari district did not get rain,
Kanyakumari
sir.
district did not get rains because that's on the southwest. I think the rain bands did not fall there. Probably.
Yeah.
Actually, if you see yesterday's rain pattern as of yesterday, rainfall statistics, Kanyakumari district is having the highest deficit with regard to NEM, minus 38%.
Yes, sir.
So,
Kanyakumari is
that has a
minus
huge-
38, sir.
Correct.
Right. So this is the problem with these these kind of patterns and systems, because the rain bands are very important, and where the rain band falls is the key. So it's most of the times when the system is kind of circulating, so one of the issues is that this particular system Burevi, it was stationary for a very long time, and it never it could never enter into Kanyakumari. So the rain bands were always near, I think that region near Tiruvarur and the Delta region, right?
Kadalur district.
Kadalur and south of Kadalur, sir. Kadalur, Tiruvarur, Tanjavur, Nagapattinam.
So
That region, sir.
yeah. So like I said, hyperlocal or not, even not hyperlocal, it's not very easy for me to tell what happens. I mean, yeah. So these are the things which are the questions for the future generation probably. Like how can we improve these predictions of rainfall um, from these systems? That has been a long-standing question. Like even during monsoon season, what happens is sometimes you get very heavy rains, even over, let's say I take a place like Mumbai. The coast of Mumbai will get let's say 200 mm, whereas as you come 15 kilometers inward, you will only have like 10 mm of rain. So these kind of spatial variability is something which we don't understand, and that is something which we have to improve, of course.
Thank you.
Thank you, sir.
Okay, so yeah, so we'll get it. So when I so I'm not covering Northeast monsoon because there is no time, but yeah, I'm just going to talk about the Southwest monsoon for the next maybe 15-20 minutes before we head to the lunch break. And this is the last module. So after that, we will get into in the afternoon session. We'll just do some what do you call looking at some charts, not charts, websites from where we can do forecasting. Okay, and then 3:30 p.m. Dr. Hosalikar will take over. So of course, the monsoon is a very important thing for India, and we have two important branches, which is the Arabian Sea branch and the Bay of Bengal branch. And both of them play a very important role in both the monsoon seasons, which is southwest as well as the northeast monsoon. So I want to actually focus on the mechanism of this monsoon or the monsoon currents. So why do we see the monsoon currents? So starting around May or around April or May, what happens is that this particular So what happens is you have this heating over land, differential heating over land and ocean, because your Tibetan plateau, which we talked about, which is now somewhere here, it kinds of starts heating up. And that heating up of Tibetan plateau is related to many factors. Like I said, the Siberian cold air or warm air, how it intrudes into this region. And the second thing is how the jet stream, the subtropical jet stream moves. So those two actually govern how this Tibetan plateau is going to heat up. Okay. And that heating up of Tibetan plateau actually causes a very strong vertical updraft, and it leads to a formation of a high pressure zone at around 9 kilometers above sea level. So you have a very strong divergence at 9 kilometers, and you have a very strong convergence at low levels. So there is a low pressure which is forming here. So what that low pressure actually does is it actually pulls your intertropical convergence zone starting from the equator to north. That is when the monsoon actually starts its process over India. So the three things that we are on the lookout for is the differential heating of the land, wherein the Tibetan plateau starts heating up, and the heating up of Tibetan plateau is again related to these extratropical dynamics that we discussed. Okay. And the second thing is we are on the lookout for when the ITCZ, which is the band of clouds that we discussed yesterday, how this ITCZ starts moving. So at the time that ITCZ starts moving, then our southern hemisphere is also very interesting, because our southern hemisphere also plays a very important role in monsoon onset, because you have something in the Mascaron Islands near Madagascar. You have something known as the Mascaron High. So this Mascaron High is over the ocean. So this Mascaron High, what it does is it deflects the winds coming from the southern hemisphere towards the northern hemisphere. So this deflection of the winds is what gives rise to your westerly patterns. And because of the Tibetan Plateau heating, these winds are pulled towards towards the Himalayan or Tibetan Plateau, and they enter the western part of India, and then they slowly move towards the central part, northern part, and then this is the circulation cell that gets this is the monsoon circulation that I'm talking about. So this westerly winds actually trigger a monsoon circulation. So all of these things have to happen together for the monsoon to arrive. Tibetan Plateau heating, the masculine high creating these low-level westerly, which is also the Somali jet, which we call the Somali jet, the formation of the Somali jet, and the initiation of the Somali jet from Africa towards India. So basically, and the location of the ITCZ, which is the Intertropical Convergence Zone. So where is the ITCZ? Where is this westerly wind? And whether the Tibetan Plateau is heating, whether there is a low pressure over Tibet, over the Tibetan Plateau. These four things are actually the important factors that govern the onset of the monsoon. So what we are on the lookout for to announce the onset is the westerly wind has reached around 30 kilometers. So these westerly winds should be very strong. So the speed of the westerly winds should be, because it's a jet, right? It's a jet. So the jet should be very strong. So it should reach 30 kilometers per hour wind speeds. The westerly wind depth should have attained 3.2 kilometers above mean sea level. So up to 700 HPA or up to 700 millibar level, the westerly winds should have set in. Because during the normal time, the winds over surface are easterlies, correct? So right now, if you look at the wind charts, you will see that the winds over India are easterlies. Throughout the India, you are seeing easterly winds, except for the northern region where the winds are westerlies. So what happens during monsoon season is the winds pattern reverse between the southern and central part of India and northern part of India. Right now, the winds over the northern part of India are westerlies. During the monsoon season, the winds over the northern part of India will become easterlies. Okay, so that is one thing that we see. So it is clearly shown in this image, right? So there is a westerly wind in southern India and west coast of India or central India, and there are easterly winds in near Delhi and northern India. So this is what is the monsoon circulation, because if you draw a circle, then you see an anti-clockwise pattern, which is a low pressure system. And this low pressure system is covering this entire India. And that means that a distinct low pressure system forms over entire India, which is going to allow the Arabian Sea branch to push the moisture, and which is also going to allow the Bay of Bengal to push the moisture. And this is the monsoon circulation that I'm talking about. The westerly winds setting over central India and the easterly winds setting over northern India will automatically give a circulation which is very favorable for the formation, for the cloud bands to keep coming in from both the basins. Okay, so this ITCZ plus the monsoon circulation is what we call as the monsoon trough or meso. So the ITCZ is the line which is the line between, is the line where your westerly winds and the easterly winds meet. So this is the location of ITCZ right now. So during monsoon season, how do I find the ITCZ? I take a 850 HPA wind chart. I'll show how to do that. Give me some time. I look at the wind and I see where these two winds are meeting, and that is the location of ITCZ. And the circulation cell is also active there. So my monsoon trough is lying around this line right now. So extending from Bay of Bengal to somewhere close to North Konkan is where the monsoon trough is lying in this image. This is how I find the monsoon trough. And this monsoon trough, which is meso, also synonymously called meso, this monsoon trough is not stationary, it will move up or down. So I have to track the monsoon trough because that is where most of the action is going to take place. Where the monsoon trough lies, that's where flooding rains are going to most likely occur. So whenever I'm talking about monsoon, I need to find the monsoon trough. And how do I find the monsoon trough? Where the westerly and the easterly winds meet and where the ITCZ is present, which is the cloud band is present. Okay. All right. So this is the criteria for onset of monsoon. Westerly wind depth 3.2 kilometers. Outgoing long wave radiation less than 200 watt per meter square. So this is the onset of monsoon factor only for Kerala, only for entering our mainland, which is Kerala. After it has entered Kerala, only for Kerala all these four parameters have to be maintained. After it has reached Kerala, as the monsoon starts propagating up north, all these parameters don't matter, because even if I don't have a westerly depth all the way to 3.2 kilometers in Mumbai, but if I have sufficient rainfall and a westerly pattern at low levels, that itself is good enough for me to announce onset of monsoon. So this is very important mistake that a lot of weather bloggers do, that the IMD announces. See, this is where I'm saying that IMD has a set rule and weather bloggers don't have a set rule, and they keep saying that IMD is wrong, IMD is no, that's not true, because IMD has clearly said in its record that this particular criteria is only for the southwest monsoon to enter the mainland. After it enters the mainland, the only thing that is important is the sufficient amount of rainfall. That's all. I don't care whether the westerly wind depth has reached 3.2 kilometers or not in central India or let's say Konkan coast. Even without this 3.2 kilometer above sea level wind depth, I can still get a lot of rain. Okay, I can still get a lot of rain through some other mechanism, which is a trough or a weak monsoon circulation, or many different regions, many different factors can give me rains. So onset, all these factors have to be kept in the mind only till the time onset has announced over mainland. After that, even if we don't satisfy this, but sufficient rainfall in all the stations, which means more than 60% of the stations have recorded more than 5 millimeter of rain. That means monsoon has entered that particular region. Okay, so that is what is the important aspect. So this is the onset for this year 2020, and one very important thing to understand is during the monsoon season. So during the normal season, this level the winds are easterly, and this level the winds are westerlies. During the monsoon season, this reverses. What happens is, in this region up to Gujarat, the winds become westerlies, and after that the winds are easterlies in the North India. So that is the shift that happens during monsoon, and that shift is very important because it automatically gives rise to a monsoon circulation. And I have already spoken about monsoon circulation because I feel like this monsoon circulation is one big parameter which actually governs a lot of things. So climate scientists are now saying that the monsoon circulation, which is persistently there for a period of 3 or 4 months in India, can affect the onset of El Nino or onset of IOD. So it is not the other way. It is not that IOD or El Nino affects this monsoon circulation, but it's the other way around, where the monsoon circulation affects these El Nino or IOD. That is what is the claim, which still needs to be kind of corroborated with a lot of evidences. Okay, so Bay of Bengal branch plays a very important role because in a season, on an average, 12 low pressure systems will form during the monsoon season. So 12 is an average. So starting from June to September or October, 12 low pressure systems should form. Out of this, more than 50% of the systems form in Bay of Bengal, which is very interesting. Most of the time what happens is the system forms in Bay of Bengal, let's say in the northern Bay of Bengal, and it always it will move along the line of the trough. So this is why the monsoon trough location is very, very important, because if I am able to find the location of the monsoon trough, and if a Bay of Bengal system forms in the if a system forms in the Bay of Bengal, then it will 100% move along this line of monsoon trough. So location of monsoon trough is very, very important because that is what governs the movement of any system from Bay of Bengal. Then, what is the role of Arabian Sea? The role of Arabian Sea is very straightforward. Once a system forms in the Bay of Bengal, the role of Arabian Sea is that it will push moisture towards this system in Bay of Bengal. As it is pushing moisture, it will form something known as an offshore trough. I don't have that here. Let me just see. Yeah. So this is the monsoon trough. This is the offshore trough. So as this system forms in the Bay of Bengal, this particular thing will bring in a lot of moisture from the Arabian Sea, and you will form something known as an offshore trough, which is one of the important mechanisms by which the entire west coast of India gets massive rains thanks to the Arabian Sea branch. So this is how the Arabian Sea branch plays a role. So even though Arabian Sea branch doesn't produce a lot of strong systems, most of the strong systems are produced in the Bay of Bengal, but Arabian Sea actually plays a role of this moisture source. Arabian Sea is the source of moisture, and especially for west coast of India and central India, because whatever comes will get advected in this way, and it will, because of the presence of Western Ghats, thanks to the presence of Western Ghats, we get massive rains. Okay, the west coast of India gets massive rains. So monsoon trough is the location where the westerlies and the easterly winds meet, plus the ITCZ location. So I have already told you that. So if you are interested in tracking the monsoon, my suggestion is that look for a system in Bay of Bengal and look for the location of the monsoon trough. These two things should be good enough for you to find out which places are going to get rains. Because if the monsoon trough is located here, let us say in this region, and the Bay of Bengal system is going to form here, then it will give heavy rains to coastal Andhra Pradesh, Telangana, Maharashtra, South Maharashtra, and also to the Ratnagiri coast and all those places, including Mumbai and Pune and all those places. As this monsoon trough shifts here, you will have a system forming in the northern Bay of Bengal, which will automatically move towards Gujarat, because your axis, monsoon trough axis, is going to be from extending from Bay of Bengal to Gujarat. This is what happened in 2005, the Mumbai floods. There was a very strong system, and the monsoon trough was very active, which was, see, the monsoon trough has a very distinct, it has a very interesting physics, because it is true that most of the systems will move along the monsoon trough, but sometimes the systems can move slightly, wobble up or down. Okay, so as that wobbling happens, it is very hard to predict which region will get affected the most. So we know that most of the regions will get heavy rains, but it's very difficult to predict which region is going to get extremely heavy rains. That is one of the most difficult things about monsoon. I can tell the picture what is going to happen. I can convincingly say that any system in northern Bay of Bengal is going to give rains to central India, including Madhya Pradesh. So expect floods over Madhya Pradesh, expect floods over Vidarbha, expect floods over North Konkan, because any system here is going to affect North Konkan directly, because the Arabian Sea branch is going to bring in a lot of moisture due to the offshore trough. But the thing that I cannot pinpoint is which places in Mumbai is going to get extremely heavy rains, or which places, let us say in Gujarat, is going to get extremely heavy rain. So that is where the uncertainty lies. So although I understand this monsoon system decently well, but again, this spatial variability is something that I'm not able to, or none of us are able to predict that. Okay, so that is where the challenge lies. So this is the monsoon circulation during summer monsoon, which is southwest monsoon, and as the monsoon fades away, this circulation moves down and it becomes weaker and weaker, and that is why you don't have a distinct monsoon circulation during the northeast monsoon. So during the winter monsoon, which is the northeast monsoon, the waves and the MJO take over. So this is the complete picture. I'm showing the Somali jet, which is the cross equatorial flow. So this cross equatorial flow is extremely important feature, because that is what is going to give you the Somali jet. So we are always on the lookout for this cross equatorial flow from the southern hemisphere to the northern hemisphere, because that is what is going to change the wind direction from easterlies towards westerlies. Okay. So this I already talked about. The location of the monsoon trough is very important, because wherever the monsoon trough axis lies, that's how the systems are going to move, and those are the hot spots for very heavy rainfall. Last thing is the offshore trough. So this is the cyclonic circulation. You can see that the winds are easterlies near Delhi, and the winds are westerlies near the west coast and central India. And this is the automatic monsoon circulation cell, which will be persistent. And this monsoon circulation cell is one of the reasons why strong systems develop in Bay of Bengal. Like all these depressions, all these deep depression systems actually originate from Bay of Bengal. Not many strong systems form in Arabian Sea. But Arabian Sea is the powerhouse of moisture. A lot of the moisture, without the Arabian Sea branch, west coast of India would be dry. So the amount of moisture that Somali jet brings in is the key for the west coast of India, where we record like 2000 mm of rain or 3000 mm of rain, which is massive. Okay. So how can you find the monsoon trough? You look for the place, you look for the line where the westerly and the easterly meet. So this is the easterly wind, this is the westerly wind. Wherever they meet, that is where the monsoon trough axis is going to lie. Offshore trough. So offshore trough is nothing but the dipping down pattern of the winds because of the system in the Bay of Bengal. and that actually is known to bring very heavy rain. And this is a very unique feature of southwest monsoon, especially for the west coast of India. How to find the offshore trough? Look at the wind patterns. As the wind patterns are showing a dipping kind of this is the wind pattern, and as they start coming towards the coast, they actually show a dipping pattern, and that's where the trough axis lies, and that's where the cloud bands form. The cloud bands always form close to the, in the Arabian Sea, and because of the presence of these strong westerly winds, these cloud bands get pushed. That is what I have tried to schematically show. Okay, so these cloud bands. So during southwest monsoon, you can see that Arabian Sea is always cloudy. Okay, so these cloud bands will get pushed because of the strong westerly winds which are present, and that is what gives rise to these rains for west coast of India, all the way from North Konkan to Kerala. Yeah, so you see this is the offshore trough dynamic. So these cloud bands will get pushed in, and that's how you get a lot of rains. So before I wrap up the features of southwest monsoon, our ITCs are moving up, a cyclonic circulation persisting over India, and winds becoming westerly. That is what is the classical, that is what is needed for the southwest monsoon onset. So you're on the lookout for these three distinct features. These are the, what do you call, the repercussions of this. So cyclonic circulation actually allows for moisture convergence. Westerly winds will always allow for a positive vorticity to get deposited in Bay of Bengal, which will create strong systems in Bay of Bengal, which will move along the monsoon trough. What is the signal of southwest monsoon ending? An anticyclone settling over India centrally. So during the monsoon season, the winds were like this. They were cyclonic. When they become anticyclonic, so basically westerlies setting over Delhi and easterlies setting over central India is the signal of end of the monsoon season. So the wind patterns reversing is the signal that it's going to end. Okay. So any doubts about monsoon? So let me wrap up, and if you have any doubts, we can have 5 or 10. We can reconvene at around 2:20 or 2:30, no problem. So I just want to show one slide before I wrap up. So we do a lot of outreach. So there is a Tech Fest festival thing that happens in IIT Bombay. It is a festival which it's an R&D festival where we have where we set up these kind of stations where we demonstrate many things. This year, of course, because of COVID, we couldn't do it. But last year we had done it, and it was actually a lot of people came, they visited, and we demonstrate small things in a tank, which is a small phenomenon of waves and these kind of things in a small tank. So next time it happens, I will keep you in the loop, and you guys can just visit. And it's a very good activity for kids because they get enthused about these kind of things. And last thing is there are a couple of YouTube channels which I am associated. I'm not promoting. This is just for your information. There's a QuestMet channel which actually we try to make very professionally edited videos. We have a professional editor who actually makes nice videos for kids, especially. Some simple 8 or 10 minutes video maximum, which tells a lot of things about what is Madden oscillation, what are cyclones, what are low pressure, high pressure areas. So you guys can take a look at it. And I have my own weather channel, where a lot of information will be available. So if you have any suggestions, you can tell me, and I will be ready to make a video and upload it on my channel. Okay. All right. So yeah, I am done now.
Can I ask a quick question on the offshore trough, please?
Yes, please. Yeah.
So what is the role played by the Western Ghats in the formation of the offshore trough?
Western Ghats actually don't play a role in the formation of the offshore trough. The only thing that actually plays a role in the formation of the offshore trough is a system in the Bay of Bengal, which pushes which allows the winds from the Arabian Sea to travel towards India. The role of the Western Ghats comes into picture in form of blocking this moisture and dumping a lot of rain over the windward side of the Ghats. So that is the reason why the other side of the Western Ghats is usually dry, and offshore trough usually favors regions which are on the windward side of the of the Western
So,
Ghats.
could one possibly argue that, say, a coastal station like, say, Bombay or Dhanu, if the Western Ghats were not present, the offshore trough would form regardless, and those stations would receive probably the same amount of rainfall that they are receiving today, whereas other stations like, say, Lonavala or Mahabaleshwar wouldn't receive as much rainfall.
Yeah, so there was one kind of hypothetical study that was done. I don't know if there is a paper published. So offshore trough will form no matter what, because the offshore trough is a monsoon feature which forms mainly because of the winds. So winds are no way kind of offshore winds are not affected because of the presence of Western Ghats. Okay. So if you remove the Western Ghats, then what happens is they found out that the moisture will reach all the way towards Marathwada, Hyderabad, and what they found was that in the absence of Western Ghats, these moisture which is coming in from the Arabian Sea has the capacity to dump lot of rain all the way up to Chennai, which is massive, right? Because that doesn't happen because we have the Western Ghats. So hence, in southwest monsoon season, Chennai only receives like 400 mm of rains. So if you remove the Western Ghats, then the only thing that will change is the variability of rainfall. So the moisture that is now not getting blocked has the free hand to move much interior. And it's due to the presence of this Western Ghats is the reason why you have Marathwada and all these places are like the drought affected region, because because the Marathwada and all these regions mainly depend on the monsoon trough axis. So any system in the Bay of Bengal moving from east to west is what these regions are actually dependent on in terms of rainfall. Offshore trough is only for giving rains to these places on coastal.
Also, the reason why we have all those rivers, right? All those, that feeds millions of people.
Correct. The rivers, most of them starts around.
The people of Chennai and Tamil Nadu, we are not looking for the monsoon. We are always looking for the breaks in monsoon because we are looking for the thunderstorms.
Right. For you, the break in the monsoon is when you get.
So when is the break? Because when it is active, we don't bother taking the umbrella or the car. We usually take the scooter.
Right.
But when it is thunderstorm, we always take the car and the umbrella. So
yeah, you're right. The break phase in monsoon over. So when it doesn't rain in Mumbai, Chennai gets rain. That is the correlation.
Yeah.
Sir,
Sridhar, this is Amit.
Yes.
Marathwada obviously makes sense. It's the extended rain shadow region and we get such less rain. But what explains the significantly higher average rainfall in Vidarbha then?
Okay. So that is again due to the presence of monsoon trough. So it's you raise an interesting point which I was going to cover. So what happens in Vidarbha or this region is the location of that. So this monsoon trough has an inclination. So starting from the west end of the Arabian Sea, west end of the Bay of Bengal, the monsoon trough is not a straight line. It always has an inclination. And for some reason or the other, this is something which I think we are researching. This particular monsoon axis trough most of the time passes through Vidarbha. Okay, and when that happens, the monsoon trough is a very important aspect because any system, any low pressure system, it doesn't have to be a strong system. Even a low pressure system actually moves along the monsoon trough, like I told you. And that is the reason why your places in Madhya Pradesh and Vidarbha actually end up getting more rainfall because your Marathwada regions are much south of it, and the monsoon trough for some reason doesn't cover these regions.
Okay.
So there is a preferential, I would say there is a preferential alignment of the monsoon trough, which is something which I don't understand. Why is that? And most of the time it misses Marathwada.
Okay.
So that is the reason. And of course, this offshore trough doesn't enter all the way up to Marathwada. So that is why this pocket kind of always a deficit, because it is not helped by this monsoon trough, and it is not also helped by this monsoon axis, which for some reason sometimes it is over Kerala. It dumps a lot of rain over Kerala, and then it swiftly moves towards this place. I don't know why it misses this region. That I still, I mean, that's something which we should think about. But it swiftly moves very quickly from this place to this place. One reason could be due to the formation of storms. If you look at historical records, most of the systems in Bay of Bengal either form in the southwest Bay of Bengal or north the Bay of Bengal. They don't form here. Last year, October was the only reason, only one off situation where a system formed in kind of this central Bay of Bengal, which actually moved along this monsoon trough axis through Marathwada, which gave a lot of not unseasonal rains, which gave a lot of rains to Marathwada in October last month, couple of months back.
Sir?
Yes.
Sir, actually, yesterday I asked one question, no, sir. North of Vijayawada only, this southwest monsoon is very active, sir. Below that South Rayalaseema and that Vellore region.
Right. So that again, I think.
What is the reason, sir? Is it due to the curvation of the coast, sir?
I don't know whether the coastal belt. See, again, I'm not a topographic, coastal kind of an engineer. I still like to pinpoint it to the dynamics, and the dynamics is again telling me that this monsoon trough is the reason why this particular place doesn't get much, because the monsoon trough for some reason misses this place. And historically, I have seen that systems in Bay of Bengal either form kind of south of it or north of it, and that is, we have to understand. So systems forming means vorticity deposition happens either here or here. So one of the things that is a question is, why is these places are the hotspot for deposition of vorticity or deposition of low pressure systems? Why doesn't the low pressure system form here near, let us say, because if the low pressure system forms here, then your monsoon trough axis will actually move along Vijayawada, Marathwada, and that will give you a lot of rains. So for some reason that doesn't happen during that doesn't happen multiple times during southwest monsoon season.
And in extreme south, sir, around Thuthukudi, Tirunelveli and all, there is a very less southwest monsoon, sir. About only 1 centimeter or 2 centimeters, sir. And only wind flows during the strong system. What is the reason, sir? In entire Tamil Nadu.
Anush, southwest monsoon, Kanyakumari, and Ghats of Tirunelveli, Virudhunagar district, they all get rains.
Yeah, they get.
But those regions that you are talking about, Tuticorin and
Thuthukudi, Ramanathapuram, that side.
No, we are on the rain shadow region from June to October. Whatever we get from thunderstorms, we should be thankful for whatever little droplets that fall on us.
Correct. Because see, again, like I said, the Western Ghats play a very important role in blocking these moist laden winds. Because if you remove these Western Ghats, then you will get a lot of rain in other places as well. But the Western Ghats block everything, and they dump a lot of rain on the other side, the western side of India. And I think we get only rains during the June to September or October. Mumbai records 2,000 mm of rain from June to September. That's it. That is the quantum, and we should be thankful because we have Western Ghats.
Sir, then why during the break phase we are getting more rain, sir, in Tamil Nadu? Is there any specific?
Thunderstorms.
Yeah, that is thunderstorms. I think we'll not mix the two, like, because that is a different. That is not monsoon system. That is more like a localized system. So let us not mix the two of them.